This sentence is worth exactly $1 million. Not for writing it, that happened in 1859, for proving it. And in 67 years, nobody has. It's called the Riemann Hypothesis. And it's about the strangest objects in mathematics, the prime numbers. Watch. 2, 3, 5, 7, the numbers that refuse to be divided, and they show up with no pattern at all. Sometimes they're neighbors, like 11 and 13, and sometimes there's a desert, nothing, for stretches at a time. Every prime looks like an accident, but zoom out far enough and the accidents start marching in formation. Here's the trick. Stop asking where each prime is. Ask how many there are below some number x. Count them, and you get this staircase, one step up at every prime, jagged, unpredictable. Now, lay this smooth curve on top of it. X divided by the log of x. Gauss guessed it at 15 by hand counting primes in log tables for fun, and the fit is almost perfect. The further out you go, the better it gets. Chaos up close, order from a distance. Almost perfect. That word almost, that's where the $1 million lives. Subtract the smooth curve from the staircase and you're left with the error. This wobbling leftover. It looks like static. Riemann's great discovery is that it isn't static, it's music. To hear it, he picked up a function mathematicians had been toying with for a century, the zeta function. You feed it a numbers, and it adds up 1 plus 1 over 2 to the s plus 1 over 3 to the s forever. Feed it 2, and the sum snaps to pi squared over 6. That's Euler, pi, hiding inside a sum about whole numbers. And Euler found something better. Zeta secretly factors over the primes. Every prime exactly once. That's the bridge. Wherever zeta knows, it learned from the primes. Then Riemann did something audacious. He fed zeta complex numbers with an imaginary part. Now zeta isn't a curve anymore. It's a landscape spread over an entire plane. And in that landscape, he hunted for one thing, the zeros. The exact points where zeta vanishes? Some zeros are boring. They sit at -2, -4, -6. We've understood those forever. The rest live in this narrow vertical strip. And these are the ones that run the show. Riemann computed the first few. The first one sits at 1/2 plus about 14.13 I. The next at 1/2 plus 21 I. Then 25, real part, 1/2, every single time. So he wrote down one sentence. Every one of these zeros lies exactly on this line. That's it. That's the Riemann hypothesis. Real part 1/2, no exceptions, all the way up to infinity. Since then, computers have checked 10 trillion zeros. 10 trillion, all of them, on the line. But 10 trillion isn't infinity. One stray zero, just one, anywhere, and the whole thing collapses. Now, why should you care where some function hits zero? Because of what Riemann proved next. Each zero plays a note. Take any zero, and it hands you a wave with its own frequency. The higher a zero sits on the line, the faster its wave vibrates. Now add the waves, all of them, on top of Gauss's smooth curve. And watch what comes out. The staircase, the actual primes, every jagged step, rebuilt from pure waves. That's the secret. The zeros aren't trivia. They're the sheet music the primes have been playing all along. And the hypothesis, every zero on the line means the music is perfectly balanced. The primes are exactly as orderly as chaos allows. That's why hundreds of theorems begin with the words, assume the Riemann hypothesis is true. An entire wing of mathematics resting on an unproven sentence, waiting for someone to close the door beneath it. Hilbert said that if he woke up after sleeping 500 years, his first question would be, has the Riemann hypothesis been proven? It's been 107 years. The answer is still no. The primes look like noise. Riemann heard the music. Someone still has to prove the tune.